Hello everyone and good time of day. Welcome to this new MLIR open meeting. Today we're going to have Ivan and Deepdrop to present their work on the Numba MLIR backend. So Ivan, the floor is yours.
Yeah, hello everyone. Sorry, and today we wanted to present our current status and our work on MLIR-based Python compiler. We presented, I think, a couple of years ago our early work. Now we have much more progress, and also we had another presentation a couple of days ago on Numba meeting, but it was more of a high-level overview. And today I'm planning to discuss more on actual implementation details of our NumPy and GPU pipelines. So let's start. I will still give a brief overview. So Numba MLIR is MLIR-based JIT compiler for numerical Python code. It has the same programming API and programming model as a Numba, where you wrap your NumPy function into special decorator, and when you call this function, it will be JIT compiled and executed native code natively on CPU or GPU. So we are using Numba frontend to pass Python bytecode, and we are also using Numba type inference. So we have a code generation for CPUs and GPUs. This includes efficient parallel code generation for NumPy functions, and also offload, NumPy code offload to GPUs. And also we have a CUDA JIT style kernel API. So in Numba, in my Numba, there is a explicit kernel API. For CUDA, we have something similar, but it's more like OpenCL API with global ID and stuff. So our current status, we support most of usual Python scalar math complex operations, support loops, and basically arbitrary control flow. And for NumPy, we support most of the ufuncs, various NumPy arrays, indexing modes, broadcasting, and also we do not support entire NumPy API, obviously, but we have a high-level API for adding new NumPy functions, which doesn't involve writing new C++ code. We also, for Numba, we also support prange, which is basically Numba API for parallel loops, parallel force. And we support code generation for GPU code generation for Intel devices. We does not support CUDA yet for other GPUs than Intel in general, but adding CUDA should be relatively straightforward in our pipeline. So here is just an example how our code looks like. So basically, you're just wrapping the usual Python function with decorator and then call it as usual. So here's an example when you call NumPy functions, and here's an example when you're using explicit parallel loops to do computations. And for kernel API, we basically have a kernel decorator and set of functions, OpenCL style functions like get global ID. You write kernel like this, and then you select global and local size and just call it like this. Okay, so our MLIR pipeline, compilation pipeline looks like that. Our input is a Numba IR, which is Python-based IR for Numba users internally. And we are using PyBind 11 to parse it from C++ and to convert it to our dialect. This, we have a frontend dialect called MLIR, which is basically currently it's intention. Initially, it was intended as a sort of general Python dialect, but now it's just basically one-to-one copy from Numba to MLIR infrastructure. And for NumPy operations, we have a Tensor dialect, which is then converted to linalg dialect. And for everything else, like for the control flow and for Python loops, we are just converting them directly to SCF. And like scalar operations, we convert to just upstream arrays and complex dialects. We have some optimizations on SCF level, and then we are just converting them for CPU, for host side, we're converting to LLVM dialect, and we are using TBB internally for parallelization, like to parallelize SCF parallel loops. Then we convert this just to like usual LLVM and compile it using org.jit. And for GPU code, we are using GPU dialect from upstream, and also we have our GPU extensions dialect, which provides like some additional extensions. And for Intel hardware, we are compiling GPU kernels to SPIR-V dialect, and then SPIR-V to SPIR-V, and then loading the SPIR-V and running the SPIR-V using SYCL runtime or layer 0 runtime. And layer 0 engine is just another low-level GPU API from Intel. For CUDA, probably we will go through NVGPU dialect to PTX to CUDA runtime, but it's like just we don't have any CUDA CUDA pipeline in the works yet, but we plan to support more vendors eventually. So, and eventually it is all converted basically to the host code. Like for the host code, we just directly getting function pointer. For the GPU code, we are generating small host code, which just like loads and runs kernels, and we get back function pointer to run it, and finally pass it function pointer back to number so it can run it. So speaking of our specific dialect, there is as I mentioned, there is a player dialect, which is just one-to-one conversion from Numba. It is currently just, we don't have any interesting transformation or optimizations on this level, and it's just immediately converted to some other some other dialects. So I will not speak much of it. For NumPy, we have dialect called Ntensor. So yeah, it supports NumPy functions, NumPy arrays, including mutable arrays, and also it supports Python ArrayAPI, compute follows data, offload model, which is basically, let's say, you can allocate specific arrays on device, and when you use these arrays like with NumPy functions, those functions will be automatically offloaded to device, and the return type from these NumPy functions also will be inferred to be device one. So you could kind of propagating this execution. And we have our GPU extensions dialect, which is called GPU runtime actually, but it should be changed eventually to just GPUX, which provides our extensions to the GPU dialect. And some time ago, I started some discussions on MLIR forums about upstreaming some parts of it, like streams, explicit streams support, and there are other things like explicit kernel loading. such I will cover it in details later. So let's start with our NumPy dialect. So our main motivation why we needed like another one tensor dialect basically was to have mutable tensors, because like there are a lot of work happening with different dialects, like Ntensor, MLIR, things like TCP and others, but most of them are using just upstream tensors, which is immutable. And for our needs, we need to support mutable NumPy arrays. So, and memref is too low level for our needs. We eventually convert to memref, but it's just, it is more convenient to have something more high level. So it supports, as I mentioned, compute follows data model when we attach device information to the array. And also it supports broadcasting on dynamic shapes, because as far as I know, in all dialects, like they're mostly concentrated on like broadcasting on. Sorry, my headset. Can you hear me? Hello?
Yeah, we can hear you.
Yeah,
Yes.
Yeah, my headset decided to switch itself. Okay, so, and we support broadcast on dynamic shapes, because at least as far as I can see, most of the work like on other tensor dialects were done on like implies like they expect that all shapes on broadcast can be deduced statically. So is it, and it's actually my question, does anyone works besides us on like broadcasts on dynamic shapes? And is anyone interested in this, like outside NumPy perspective?
So what's your question exactly about the broadcast? If someone is interested in what?
So is anyone using, is anyone working on broadcasts on dynamic shapes in different dialects, like in HLO or something else, or TCP?
I mean, as far as I'm aware, like both HLO side, TensorFlow side, PyTorch side, there is this representation. I mean, I think there's some limitations with respect to the different codes and backends for these, and you know, like this. But I think there's definitely interest. I think that the interest also differs if you're talking about ones that changes rank or not. If it's just like the old style one broadcast, you know, kind of category. But I mean, there's a lot of the front ends that produce such things, and so a lot of the objects are represented. Codegen wise, I think it's a little bit more potentially like inconsistent, you know, exactly the support here. But yeah, I mean, I think folks are interested, if that's the question.
Okay, yeah.
It would be interesting to see indeed how you handle it in the compilation flow.
Okay, yeah. So let's go next. It's our tensor type or Ntensor type. So it's like usual shape type derived from shape, and its usual interface. It's always ranked for now because we don't have use case for unranked yet, and it have format like shape, layout, and device. So shape and type is just usual shaped type thing. Layout, currently layout we have like NumPy style, like contiguous or any, but it's it's really a hack, and let's use it in a single place in the entire pipeline and ignored by most of the cases. And I hope they'll get rid of it. So let's think it doesn't exist. And we also have a device, which is just a arbitrary attribute we can attach to Tensor. And it basically, for our compute false data model, it's just describes on which device we should execute operations. And in total, it will look like that shape, layout, and device. And speaking of Tensor operations, basically we have two sets of operations called one of high level and second one is low level ops. So high level ops, they are intended to be emitted by the front ends, and basically they support various like numpy or Python features like named and emitted parameters, and it's like they are really designed to be close to initial, let's say, numpy code. So they support output parameters for numpy functions as well, and various fancy indexing modes for arrays. And there are lower level ops to which they are converted eventually. So for level ops, all parameters are positional, all parameters are explicitly stated, so we don't have omitted parameters. And array indexing is explicit, and it's have a set of load, store, subview ops similar to like memref dialect, and all fancy indexing like -1 indexes, toxes, last element, and such handled on the handled explicitly. And also we does not hard code any specific set of ops from numpy or from ArrayAPI. We just have a general way to specify op, and user can add any op he wants. And we needed this because all ops defined in basically in Python code dynamically. It does not hard code anything in Butygin files, any specifics. Okay, so let's go. Here is some example of layering. So we have a simple function when we have array with slice, and we assign some value to the slice. So first of all is our apply frontend dialect. So it's pretty straightforward. We're calling build slice, and then calling set item, which just takes array, slice, and value we are setting. And this was the frontend dialect, and after converting to the Ntensor dialect, it becomes just Ntensor set item, which is straightforward. Takes array, slice, and value. But this is set item. This is high level op, so it can be, let's say, those slice arguments, they can be omitted. For example, we have a step is omitted and implied 1. We can have negative indices, and they will be handled properly. And then we are converting to the low-level ops called. So what we are doing, we have an op called resolve slice, which takes slice and shows size of array, and its return values actual begin and size values, which are adjusted to the actual array bounds, and all these negative indices and such handled on this stage. So next we have a subview, which just follows memref and tensor conventions. We have a Ntensor create, which create temporary tensor, which value, and then we have a Ntensor copy, which copy like assign, do the actual assignment. And then this copy converted to linalg, and for copy specifically, we are converting this to mixed linalg when we have input as a tensor and output is a memref. So this is like array we are assigning to. Okay, for Ntensor operations, we have I skipped the frontend dialect, so directly for the numpy operations, we have Ntensor call, high level op. So we have a actual op as just a string attribute, and it have one argument here, like size, returns new Ntensor. But after we convert them to the low level ops, we have Ntensor primitive, which have like one actual argument, which is size, and 3 more arguments which were omitted in the original.
Can I ask you a question, or do you want to
Yeah.
wait for questions till the end?
Yeah, go ahead.
Is these two call primitive pair, this pair of call primitive, does the first one, I mean, the first one sounds like it calls into the Python runtime. But I guess it doesn't, because the second one has.
It doesn't.
Okay.
I like second one doesn't call into numpy like runtime either. Yeah, maybe Tensor call not the best like name, but
NumPy op or something. But anyway, I get it.
Yeah. So there is all omitted parameters are stated explicitly here, and so originally we have only size. I think for arrange parameters are begin, end, step, and d type. So here they are stated explicitly. So the actual labyrinth of this numpy arrange doesn't, so it don't need to care about if we have some omitted parameters, or like we have parameters in different order and they are named and such. So they have a actual labyrinth have a stable API to work with.
Gotcha. Cool. Thank you.
And then we are loading this to linalg generic, which is pretty straightforward. And for this case, when we have numpy primitive, which takes some arguments, which may be like just scalars or another numpy arrays, and return a new array. So Ntensor primitive always return a newly allocated array. So we can convert it directly to linalg generic on tensors. So it's like compute indices and return a new tensor. And then it's converted to it's converted to memref, because we are using memref as a ABI between function calls. Okay, so let's more another example when we have an output parameter for the numpy function. So again, we have a first Ntensor call, which have a named parameter out. We have 2 positional parameter and 1 named parameter. And at this stage, it's just named parameter. We don't have any knowledge here. It's actually out parameter. But it's handled later. And when we are converting it to the primitive, it's actually it's first converted, generate primitive, which returns a new tensor, and then we are doing a copy from this newly allocated tensor like to the actual out tensor, and it's like, and we rely then when everything is converted, like this primitive and this copy converted to linalg, it will be fused either on linalg level or later on loop level. And there is another important point, and Tensor call doesn't have any side effect interface attached, and it's considered that it can have any side effects, so they cannot be just optimized away. But for the specifically for the primitive, it's always pure, so they can be removed if a result is not used, or they can be like subject to common sub-expression elimination if you have like multiple calls with same arguments, such. And copy obviously have a side effect of that it reads from input array and writes to the output. And then it's just converted to linalg, and we are using like upstream linalg fusion process, and it's just fused nicely to the single linalg generic op. So about details on our numpy layering. So basically we have a layering to the linalg-on-tensors, but as our arrays are mutable, we cannot just lower everything. So we have an analysis which basically allows this layering only if like, we can prove it's safe. And in most and for now we just check. For some ops, we just check we don't have writes to the output of the ops, and we are using local alias analysis from upstream for this check. So we basically, if I remember correctly, we just collect all writes, all potential writes from the function, and then check using local alias analysis if our result is aliasing with any potential writes. So copy ops, as I mentioned, layered to the mixed linalg when the output is memref. We are using element-wise fusion patterns from the upstream for the optimization, and after all linalg-on-tensors are loaded, and if we have something remaining, so everything else will be loaded directly to memref instead of tensors. And also, as I mentioned, layering is defined. Layering logic is defined in Python. So here is example of how our layering API looks like, and it's basically a high-level wrapper above linalg builder. So we have a two-dimensional dot as example, and we construct the usual linalg generic with iterators, maps, and inputs, outputs, and body, and just emit. It's not exactly one-on-one mapping to the linalg builders. It is slightly more high level, but it's generally follows the same logic. And we have some other APIs for this layering. We can just insert a call to some external library, or we can just inline a chunk of Python code which will be executed directly. And this inline code can include basically any feature we have, like pre-range loops or some calls to some other numpy functions, and it will work. Okay, so a few words about our bufferization process, because as we basically result of our lowering is a mixed Tensor memory of code. We cannot use one-shot bufferization, so we are using legacy bufferization, dialect conversion-based bufferization, but with some additions. So specifically, we have a op called change layout op to avoid data copies in some cases. So for dialect conversion bufferization, there is an issue. For example, if you're lowering Tensor extract slice to the memory of sub-U, basically dialect conversion expects that you have a Tensor with identity layout both as an input and output, and memory of sub-U generates memory of with threaded layout. And in existing upstream bufferization, it's handled by basically inserting a copy. But in our case, instead of copy, we are inserting our change layout op, and this change layout op have its own set of patterns, which is basically propagates it through the memory of operations. And in most cases, we are able to basically to completely get rid of actual copies. So basically, when we are doing bufferization, we optimistically assume that like all memrefs will be loaded to the identity layout memrefs, but while this change layout op propagates, it changes layout if needed to the actual layout. And I think it's much simpler than one-shot bufferization, because basically you have all your bufferization decisions are local, and also all your change layout propagation decisions are also all local. So, and it works reasonably well for us. Okay, so, and here is example. Let's say we have a sub-U which returns threaded memory of, we inserting change layout, and then we are doing just load from this result. And this change layout can be directly like merged into this memory of load when we are doing load directly from the threaded memory of instead of identity. And most of this change layout operations is like this. But we have also some patterns to propagate this change layout through the control flow ops, through the SCF ops. So yeah. And speaking of broadcasting, so let's see this simple example. We are adding to numpy arrays, and basically in actual, so first we're generating this straightforward, we're generating call first, then straightforwardly converting to this Tensor primitive op, which expects to Tensor, but in numpy, so one of these arrays can have some dimension as 1, and second one some different value, and you need to broadcast them. So what we are doing, we are generating special, when lowering this Tensor primitive to linalg, we are generating special op called broadcast, which takes like all arrays which needed to be broadcasted and return a new array. And so how we actually going to implement this broadcast? So first of all, we had a naive approach. Basically, when we compute the resulting dimensions, we needed like for all arrays, and then for each arguments, we broadcast in each dimension individually, and then combine or build a long chain of this individual array dimension expansion. It's generates functionally correct code, which returns like correct value, but obviously it's very slow. It can produce multiple copies for each argument. It doesn't allow any fusion, like it blocks any fusion between, like if you say you have some result of on one numpy operation used and the other to the other. And so, but here how it looks like. So we have an input argument. We check if like dimension 0 is 1. If dimension is 1, we expand the specific dimension, and if it's not 1, we just return argument. This is for the first dimension. For the second dimension, like we are doing exactly the same, but just using the result of previous expansion as the input. And then finally we are using the final result. So, and for each one of these specific ifs, we just lower to linalg generic with maps when one of the dimensions map to 0 for the array we need to broadcast. So how can we improve this? First of all, as we have a JIT compiler, we actually can change how functions are dispatched. And basically we are dispatching two versions, well, multiple versions of function, depending if some of the array arguments are equal to 1 or not. And basically if it's equal to 1, my headset. Hello.
Yeah, we can hear you.
Yeah, my headset again disabled itself. Okay, so we are dispatching a separate version of function for the array size of 1, and in this case we are setting array like size specifically statically to 1, and it allows to fold this at least for when the static size is known to 1. It allows to fold this if and it will be fused, but it won't work for the remaining case. When it's not equal to 1, we will still have this dim, this if. And in this case, we have another analysis called shape range propagation, and it's basically in upstream MLIR there is an integer range analysis, which basically attach range information to the integer types and propagate it through the operations, and it can be used to optimize like comparisons and such. And what we did, we extended it for the shaped types, and we propagate shape range individually for each dimension for the shaped ops for the shape types. And basically in addition, when we have arrays as input and size is not equal to 1, we set a custom attribute to the function argument, which have this actual range of dimension sizes, and this information is propagated through the our ops, and it's on the dim ops, it is converted to the existing integer range analysis, and it is used to eliminate these comparisons, even if like dim is not equal to 1. But we know what we can determine statically, that is, it doesn't equal to 1. Okay, and it works reasonably well for us. So yeah, any questions?
I don't know how the rest of the folks in the community and on the call feel about this, but is this upstreamable? I mean, it seems pretty useful for anybody else dealing with shapes.
Yes, it's upstreamable, but it needs some work, because for now, so for the existing integer range analysis, there are an interface which basically defines how, based on input arguments, how to propagate range to the outputs. But for our case, for now, we just hard-coded list of ops we are interested in, and it works. So we probably need to design a new interface to handle this specifically for shaped type, or to extend the existing integer range interface to be able to handle the shaped types. But yeah, I think it's pretty much upstreamable, and if someone interested in this, we can work on it.
Cool. I'll reach out to you about that.
Okay, we have.
Yeah,
next is our GPU.
Sorry, one question perhaps. You mentioned fusion. So
yes,
how does this now enable you to do better fusion? Because one of the problems with broadcast is always that you don't actually want to materialize, right?
So for broadcasts, even like after we eliminate these ifs, we will have this expand op as a linalg generic, and we will have the sequence of linalg generic which expands individual accesses of the arrays, and existing element-wise fusion patterns is able to fuse them into actual generic op, which is actual numpy op implementation. So in most cases,
does this get fused into its consumers? So this conditional, right? The linalg generic op in here that actually materializes this. Is there any fusion happening with that op?
Oh, sorry.
So, at the moment here we have the explicit materialization of the broadcast inside that body, in the den body. Is there any fusion happening with respect to that as well, or is this still now resulting in you have a conditional where there's explicit materialization along the prep?
Yeah, like the only thing we are doing is like removing these conditions, and then we are relying on the existing fusion to fuse everything together. If it's, I'm not sure I understand the question.
Sounds good. We can follow up. I mean, I think that the GPU one will be interesting as well.
Okay, but I think we probably have like 10 minutes remaining, so probably we should. Can we continue on next week? And so can we continue next week? And today we just can answer the questions.
I don't know how much content you have more, but we can pick it up next week if there's not. Yeah.
I think it's about half of all slides. So yeah, we definitely won't fit in 10 minutes.
Do you have examples of the fusion? Like if we cut it in two, then we can stop here and we can talk maybe a bit more about the fusion, or maybe next week you can come back with some examples of the, a fusion with the broadcast. Like the question Jacques was asking is one I was asking myself as well, and it would help me to see an example, of this.
I don't have. Well, do you expect, like, do you want to see actual MLIR IR, how it looks like?
Yeah. I mean, you showed something with two SCF if, and I guess the question was like, then do you do like first if fusion when you would have, for example, here you cannot fuse, of course, but do we expect that at some point we have a if dim0 = 1 and another if dim0 = 1, and we fuse the two if, and then we can fuse more? Or
so we expect that after our passes, which shape range propagation, we won't have any SCF ifs here for dims, and we will have just linear sequence of linalg generics.
I see. So it's all tied to the range analysis. I see. Okay.
Yeah. So I don't have code on hand, and it's quite big to be included in slides, but I can construct it, and we can discuss it on forums.
Yeah, even with a pseudo example, like you can simplify the IR, but yeah, that's always useful to understand the mechanic of how things fits together. I don't know if anyone else has other questions.
I mean, I perhaps have one here. So, I mean, when you say that this cancels out, so are you also considering dynamic shapes and dynamic dimensions along this,
Well,
or is this the static shape, but it's the one?
Well, our shape range propagation, this is specifically created for the dynamic shapes. Because for static shapes, we can just directly propagate the actual shape value and use it directly. But for dynamic shapes, we are propagating possible shape range, and it's being used to eliminate these comparisons. Is this answer your question?
Makes sense.
Yeah, but I just don't know with that how you'll always get rid of the if. I mean, it seems like you will need to materialize this if in some cases then with this setup.
Well, there are cases when there are probable cases that this if will remain in code, and especially if you have some long chain or some complicated ops. You have some complex code, and this SCF if may remain, but yeah, this will be unfortunate and it will be slow, but at least we will still get a correct code at the end, which return correct result.
Yeah, makes sense.
I have a question about the JIT philosophy approach paradigm here. So I believe that Numba JITs at the essentially decorated level, where it's not JITting any particular call that's in a function that's being decorated, unless there's a function call in there that is also decorated, right? That is also a call to a function that has been decorated.
So for Numba, there are two modes actually. You can explicitly specify types you want to compile this function for, in decorator itself. And in this case, it will be like compiled immediately, I think. But when you have decorator without any actual types specified, it will be compiled basically with the types you provided on the call.
Okay, so that makes sense. The thing that I'm wondering about is inside of a decorated function, you're not jitting those calls. That entire function is, when called, jitted, compiled. I shouldn't keep using jit, but like, so I decorate a function. I can't put a breakpoint. Like, this is the experience that I've had with Numba. If I decorate a function, I can't put a breakpoint in the function because that code has been disassembled by the Numba JIT thing that extracts the bytecode that blah blah, right? So
you mean setting numpy breakpoint, like
there's a
to
Python breakpoint, yeah.
Actually, I don't know. Actually, I don't know how is the Python breakpoints is they supposed to work from functions, from JIT compiled functions. You can, yeah, I never checked it actually, and it won't work in our pipeline definitely, but you.
Well, I mean, I know how the breakpoints work. There's a set trace API, and you pass it essentially a line number or something like that. Well, but the question that I have is, an entire decorated function by an njit decorator is compiled, right?
Yes.
Yeah, that's basically it. Yeah.
Actually, you can potentially convert Python breakpoint to the native breakpoint, and on the in the wrapper, like in the JIT wrapper, convert it back to the Python breakpoint, something like that. But probably unlikely if it's actually implemented in Numba.
Yeah, it wasn't the breakpoint. The breakpoints were like an illustration of my confusion about how Numba worked. I was mostly wondering about, in what sense is this jitting? It's essentially like, I'm not trying to be argumentative, but it's not jitting, right? You're compiling an entire function.
Yeah.
It's from the Python programmers or runtimes perspective that function is just in time compiled, but the function itself that you decorate is entirely compiled.
Yes.
Yeah. Okay, cool. Thank you.
I'm going to present our GPU pipeline, how it works. So first of all, how we actually accessing GPU from Python side. So we are following compute follows data model from the ArrayAPI when you're allocating arrays on the GPU, and then when you do call numpy operations of the array on the arrays, the result of those numpy operations will also be GPU arrays. And basically, you propagate your GPU information through the ops. So here is a simple example. We have a library called dpcontrol, which can allocate arrays on GPU and also can do some general GPU tasks like enumerating devices and such. And here, I should probably wrote device equal something, but here this will dpcontrol dpt1s will allocate array on default device, and then we are just passing this array to the function, do something with this arrays, and basically this addition, like 8+1, will be also executed on GPU if input array on GPU. So, and how it looks in IR, we are still using our Ntensor types. but now we additionally have a device description attached to the type. So we have this device equal level 0 GPU 0, which is basically a backend, which is used by. So we will eventually offload it to SYCL, and this is basically just describe backend, which will be used by SYCL to execute code. So here we are taking array, a GPU array, we are calling binop plus our array plus constant and returning a new array. And here still the return array does not have a GPU descriptor attached. So we need to propagate it. And the idea is we have a special path. So initially, the only types we have with GPU descriptor is the input types. And then we have a special path, basically, which is based on MLIR upstream data flow framework, which is basically visits ops and tries to propagate this device information through the all ops. And so until the return array. So, and if some op have conflicting like inputs, let's say if we have numpy add with arrays on different devices, it is considered an error, and this path will return error. So next, how it look like. So generating tensor primitive first without return type device, and then after this path we just like converted it this tensor primitive, but its return type now have this GPU description. We're still casting it away while doing return, but it's basically just for some API issues, API reasons. If we call this function from say some other function, from other JIT compiled function, this type will be casted back to this type with a GPU description. So, but now we have a problem because we want to lower this primitive to the linalg-ops, but we also need to preserve this GPU device information in some way in IR. And for this, we have a special op called environment region op. And it's basically, it's similar to, let's say, SCF execute region op. It's just basically control flow which just executes its body one time, and so it can capture values from outside. It can yield values from its body, and it allows basically to wrap any code into this op. And basically, when we are generating linalg code, it will be wrapped in this region ops, and it's, for example, it prevents some undesired optimizations. For example, if you have some op on GPU and some op on host, and they are like, well, that's sort of synthetic example, but if they are used result on another, but if, let's say, GPU op in its own region, like it won't be fused because like its value will be yielded from our region op. So, and this region op have this device info attached to it as a attribute, and also those regions can be nested. Like how exactly to handle nested region, depends actually completely on the passes how to interpret this. But for our cases, for GPU library, we are just using innermost region, and also those regions some have canonizations on them, where like to remove empty regions and such. But one of the most important optimization is that we have a pattern which merges adjacent regions. So if you have, let's say, if you have multiple numpy operations which call which uses previous operations results. So initially they will be leveraged to the separate environment regions, but those regions will be then merged together into one big region. And so this is how it looks like. We converted all our Ntensor types to memrefs. We have a linalg generic, and now we just we have this linalg generic wrapped in this region. So, and this linalg generic will be eventually offloaded to the GPU. For ops which are not wrapped into regions, they will be executed on host. Okay, and then
a question just in the environments. Because I was thinking about the nesting, like in which case do you end up with like nested environment where you would have like different device?
Well, I don't like, we can't generate nested regions with different devices yet. Like we don't have such scenario, but we have scenario when we have like nested regions on same device. And actually in this case, there is a canonicalization when basically it will take outermost region, just take outermost region and drop all innermost. If they have.
How this happen? Is it like when you have function call and inlining? Or like what do they come from basically?
Yeah, the inlining can be one of the cases. Yeah, actually, I think it's the most common case, because when we are leveraging linalg generic ops, well, when we are leveraging numpy ops to linalg generic, what we are doing first, we are generating linalg generic, and then the generic have a function call inside its body. And then this call is inlined. Oh, yeah. So I can't think, there are probably other scenarios, but I don't remember exactly right now.
That's good, thanks.
So going next, we are not leveraging linalg ops directly to the GPU. We are first converting them to the SCF parallel ops, and one of the reasons for this, because there are cases when we want to lower SCF parallel to the GPU and we don't have linalg. For example, we can have p-range inside the function, which is parallel loop, and we also want to lower them to the GPU. And in this case, we won't have any linalg ops. So we are learning from the SCF parallel. We may think we may consider at some point to lower directly from linalg, but at this point we decided to just always lower from SCF parallel to simplify the code, as we need to support SCF parallel anyway. So, and we have a null generic for two-dimensional memrefs. We are converting it to, it is converted to the two-dimensional SCF parallel, and which is still wrapped into this device environment region. And then, but in upstream, there are passes which flowers from SCF parallel to the GPU, but they are naive. Let's say if we have, like, I think they are just straight lower to the, like, first argument to the blocks and second argument to the threads or something like this. But in our case, and it won't be very efficient, but in our case, we have a special pass which transforms this parallel. And basically what we are doing, from this parallel, we are generating 6-dimensional parallel when outer 3 dimensions will be mapped to the blocks. Next 3 dimensions will be mapped to the threads, and we have a special op called suggest block size. It basically each takes a global size and then return a suggested block size for each dimension. So, and we transform loop this way, and we insert like proper calculations to calculate linear index back, and we insert a proper like bounds check because when we are splitting this into blocks and threads, it's basically, it will have the total iteration count will be blocks multiply threads size, blocks count multiply block size, which can be bigger than our actual size. So we insert proper checks, and also we insert proper GPU mappings between individual dimension to the actual GPU dimensions. So first 2 dimensions will be blocks, and next 3 will be threads. And in this case, we had a 2-dimensional loop, so we converted. We took first 2 dimensions as a like proper iterations, and the second dimension is just size 1. So if loop have more than 3 dimensions, we'll take only 3 outermost dimensions, and other dimensions will be just loaded sequentially inside the, like, on GPU. And then in this stage, we are just using, I think we are using just upstream for SCF parallel to GPU pass, which converts this SCF parallel loop to the GPU launch op, while mapping loop iterations, loop indices to the GPU indices according to mapping we set. And this GPU launch is still wrapped into the environment region, which will be used later. Okay. And yeah, a few more words. So in our pipeline, we are layering for Intel devices, we are layering GPU kernels to the SPIR-V, and then like compile the SPIR-V using as a SYCL runtime or Intel Layer 0 runtime, which is just another low-level GPU API from Intel. So, and for this specifically, one of the conversions we need to do is when we are converting to the SPIR-V, and we are converting to the kernel flavor of the SPIR-V. Basically, we are converting memrefs to the bare pointers without any sizes or strides attached, and so we can only convert, like, we cannot use dynamic strides sizes directly in calculation. So to be able to lower this, basically we have a special path which converts all memrefs to the single dimension memrefs, and then just do this index calculation. Like it extracts traits and sizes, and then do this like explicit index calculation on one-dimensional memrefs. Okay, so next we are outlining this GPU launch op to the GPU launch func. Basically, when we have a kernel body as a separate entity, we are using mostly upstream infrastructure for this, but one addition, then we have to update this our suggest block size op, and now this suggest block size op also have a, so GPU launch func op have this reference to our outline kernel, and GPU suggest block will also have this reference to the kernel. And it needs, because in Intel GPU runtime there is a function actually which allows you, if you have a compiled kernel, you can like pass a expected global size, and you can ask driver to get a preferred local size for your global size and kernel. So we need to pass kernel explicitly to this function, and because of this we are updating this suggest block size. So next we have a GPUX path, which is, so some time ago I created a post for MLIR forums about adding explicit stream params to the GPU ops, and this is like exactly where we are using it. Basically, we are converting upstream GPU launch func op to our launch op, but in this case we are adding an additional op called create stream, and basically we are explicitly creating stream and using this information from the environment region, like device from environment region, to this create stream. So we now have explicitly created it on some specific device. Then, and we are passing it explicitly to the launch kernel. And also another change we have, that in this, as a upstream launch func takes kernel as a symbol, but in our case we are doing the kernel loading as explicit operations. So we have a load module function or op which takes a symbol to the kernel and return a SSA value, which is basically a reference to module. And we have GPU kernel, which extracts from this module a specific kernel. And we also pass this kernel explicitly as a SSA value to our launch kernel op. So after we do this transformation, we now have this device information explicitly captured in this stream value. So, and after this transformation, we don't need this device region anymore, and we can remove it. Okay, any questions? Okay. So this code, it will work. So, and later, we are, as I said, we are leveraging this launch kernel, load kernel, like load model and such. We are leveraging it to calls to the SYCL runtime and SYCL runtime under the hood. Like for Intel devices, it has like layer 0 or OpenCL backends. There are also support, like SYCL also support CUDA backend, but it can consume SPIR-V. It needs PTX, I think, and we don't support it yet. But I think eventually we'll try to support it as well, like to support CUDA in this way. And yeah, and we updated suggest block size another time. In this case, we are passing GPU stream and loaded kernel explicitly as FSA values as well to suggest block size. So this code, it will work. It will return like correct result. It will run on GPU successfully, but it will be actually very slow because each time we are calling this function, basically each time we will create new GPU stream, we will load kernel. We'll load kernel like in the stream, which is very slow actually. We'll do calculate like actual computations and we'll then destroy kernel and stream, and it's very slow. And, like compiling SPIR-V kernels like by driver is very slow. So we have some passes to optimize this and basically to cache those compiled kernels and streams. So first stage of this transformation, we are taking this function and just outline this initialization and deinitialization to the separate functions calls. So here we have like separate function with create stream, load kernel, get kernel, and separate function with destroy kernel and destroy stream. It doesn't like, it still directly calls this function, so it won't be performance improvement, but it needed for next passes. And we are also attaching special attributes to those outlined functions, like outlined init and outlined dinit, so next passes can understand it. And next pass, which is we actually convert this direct calls to this init and dinit functions to the our special ops called take context and release context, and which takes this function as a symbol to this function. And basically what we are doing when we are loading this take context to the LLVM, what we are doing, we are creating a global, well, first we are declaring a struct which contains all these like values we want to cache. It will be stream, module, and kernel in this case. And we are creating a global variable which is pointer to this struct. And basically, when we are loading this take context, what we are doing, we are checking if this variable is null pair, then we allocate this context using this function. And if it's not null, we'll just use the cached values. The release context, it's actually currently the release context does not release anything, but instead what it's basically doing, we are doing when we are allocating this function, these values for the first time, we are adding this allocate functions to the global destructor list. And when everything is destructed in this moment, everything will be actually deallocated. And in our like Python JIT case, it will be when the object, like JIT function object, Python object is deployed. Okay, so last part, and yeah, and this basically mostly all for the GPU. We are leveraging kernels to the SPIR-V. We are serializing them. We are loading it using our SYCL runtime, and we are leveraging all our custom functions to to the close to this SYCL runtime. So, any questions on this? There were some questions in those old thread we created on adding this explicit stream parameter to GPU ops. Is this does I answer your questions? I think it was you maybe.
So I guess the question is how do those stream get managed is, or there is I'm not totally sure yet. I would have to think a bit more about it. How do the stream gets materialized, created, and what do they imply? I would have to go back to the discussion and to the RFC. I don't remember all the context. I remember we had a discussion and I said it would be great to discuss live about this, but we should probably have a dedicated discussion, on more of a dive on exactly this topic and what you model and how they get introduced.
I can compile I can compile a simple function, create a full log IR dump after each pass. I didn't to show how it get transformed by each pass, but it will be way too big for any slides.
I think the discussion we had on Discourse were a lot about layering and abstraction. The GPU dialect was meant to be an abstraction of the platforms. So it's intended to be something that higher level compilers can emit, and then we can target various platforms. We can lower it to Vulkan, we can lower it to CUDA, we can lower it to level 0 is the name of your platform. I think. And then the proposal was to add an optional stream thing, and that became interesting because it was are we bypassing an abstraction level? I think the questions were around this, but I would have to go back to the discourse threads because I don't. I don't the details.
And my idea was specifically make this optional, so all existing, say, CUDA leveraging will still work as it is, and I'm not even sure if it's a good idea to actually update existing CUDA leveling to this new stream API. But actually, if we in our case, SYCL runtime, if SYCL runtime supports CUDA backend, it will just work. Our entire pipeline will just work as is for it with this stream.
Yeah, I'm obviously not asking you to implement, the support and the lowering for every platform, right? It's more about when we design thing, I'm trying to think how we will in the future implement it. I think the GPU team at Google, when they implemented the GPU dialect and the async dialect, the idea was to express dependencies with tokens, and then mapping to stream would be a lowering. So the idea was that the abstraction exposed to higher level would be you expose dependency graph with token, but you don't allocate and deallocate explicit streams in the GPU dialect. This is a process that is done as part of a separate lowering. And so I guess
Yeah.
if I remember correctly, my question was like, what kind of, and that's what I remember. I'm slowly remembering the questions, right? The question was like, what information do you have that makes it that you can do better job at allocating stream than we would go from a list of dependencies with token and be able to do the same thing?
Well, in SYCL case, like having like in SYCL case, we have a queue with a separate object, and we have a like separate, and it have a separate dependency management using events. So basically, you can have a queue, but queue can execute, like you can submit kernels to queue, but queue can be asynchronous, and basically kernels can be executed in any order, and you have to explicitly specify dependencies between kernels, even if they submitted to the same queue. I'm not sure if the like direct analog in CUDA for this.
There isn't, as far as I know, but so if you have this, why do you need multiple streams?
Well, in our layering, we can potentially have like we can potentially have arrays on multiple GPUs, and each of those arrays can be like it will generate a separate device region, environment region, which will be layered basically to the separate create stream, and we will have like multiple create stream ops for each GPU. And
it's like one per GPU, you mean?
Yeah.
I see. But you would have
we can potentially even have like one stream for the, let's say, discrete NVIDIA GPU, and one separate stream for the Intel integrated GPU, which are running in parallel and on different backends.
So at this point, the stream is more a concept of almost device assignments.
Yes, and I'm not even sure if a stream a good name for this object. Sure. Like in this proposal, we have a separate object called a device, and separate type called a device, and separate type called a stream. I'm not sure if it's like, and we create stream from device, sort of, but I'm not sure if it's like good idea. Probably we can just rename this to create device and call it device and pass it like as a device directly.
I see. Yeah. There are questions around, when we start talking about streams, which are like are streams in order, out of order, or do kernels need extra synchronizations? In the CUDA model, what the terminology of stream is really in order queue, and you only use events to synchronize across multiple streams. So the streams are really are the only way to execute multiple kernels concurrently on the same device, for example. So that's what streams mean on CUDA devices. And I'm not saying we have to adopt this terminology. That was just to provide context in terms of.
Yeah. On Intel, on SYCL, and on layer 0, basically, you have like queue object, but queue can be either like synchronous or asynchronous. And in synchronous mode, it will work like the same as the CUDA stream.
Got it.
But in asynchronous, it will be like potentially execute kernels in any order.
Yeah, those were queues in OpenCL as well. They could be in order or out of order.
Yeah.
Makes sense.
Okay,
Is it the end
and
of the slides? I don't know.
I have a few more
more
slides, but not much.
We have time.
So, how much time do we have?
We have 20 minutes left, so that's plenty.
Okay, so the last part specifically on GPU, the last part is that not all Intel devices are supporting float 64, and if we lower like directly, we will get a error. So we have a special path which is optional, and it can be enabled or disabled in our JIT decorator by user. So we have a special path which can truncate all float 64 computations in kernels to the float 32. And basically, for most part, it's just like directly truncates all arrays operations to the float 32, directly converts all arrays computations to float 32, and it runs before conversion to the SPIR-V. So let's say if we add a PTX layering, it will still work. One of the interesting part is when we are passing float 64 arrays inside the kernel and how to handle them. One of the potential solutions was to just copy arrays before kernel and then after kernel copy them back, but the thing get complicated when you have multiple arrays which are views into same array. So we decided to go another way, and basically what we are doing, we are interpreting this memrefs, like float 64 memrefs, as the memrefs of vector of 2 int 32, and then in GPU kernel we are using like arrays bitwise ops to basically to manually convert this float 64 to float 32. And for this we need an op to do basically to do a bitcast between memrefs of different element types. In our case, between memref of float 64 and memref of vector of 2 int 32. I created a thread a few months ago discussing adding this memref bitcast op to the memref dialect, but like we didn't find a, let's say, satisfactory solution to this. So we should probably return to the discussions. Okay, that's all on the GPU part. I have a few more slides on some smaller parts of the pipeline, which can be interested, like to outside of our project. So, okay, so one of the things we are using Numba as a front end, and Numba outputs the IR as a CFG form, but in our pipeline we are using SCF everywhere. Basically, we rely that the entire code in the SCF form, and we had previously we had our own path to convert CFG to SCF, but we recently rewrote it based on the paper, and I think like in this paper they have a proof basically that like it works good for us, and I think in this paper they have a proof that basically they can convert any CFG to the structured form. So I think it can be interesting like by itself. And in this library we first convert loops to the SCF file ops, and then we have multiple stages basically when we have uplift SCF file to SCF4 if it's possible, and then uplift again from SCF4 to the SCF parallel if it's possible. Okay. Next part, that we have some custom memory handling for the memrefs, basically to have interoperability with Numba and numpy arrays, which are reference counted. We have to use basically to make to handle our memrefs also as ref counted. So basically we have a custom ops to lower memref allocs and memref dialects, and basically what we are doing. So memref object itself have a two pointer to the allocated data and pointer to the aligned data, and actually only the aligned pointer is used for the actual accesses for the memory of data. So in our library, we are using this allocated pointer, but instead of storing just pointer to the allocated data, we are storing pointer to the control block, which holds like reference count and some additional info. And we have our custom retain op, which is converted from memref clone. So memref clone bufferization or buffer deallocation process can generate memref clone. We are converting this memref clone to retain, and this retain then converted to just basically incref, to which calls, which increments, just increment reference count on memref. And this
this because clone is supposed to be a full new copy, like the original could be then written.
It's interesting. Actually, this path is quite old. I'm not sure about current definition of the memref clone, but at least some time ago, I think it was described in a way like that it can either be like if it can either use same memref or copy it, and it's basically up to library to decide.
I mean, it's weird because I don't understand what would be when would it be useful to have a memref clone if the memory is not copied? Like what would be
I think the use case was, let's say if you have
because also like you have to know if you need to free the memory or not, right?
I think I can construct an example. So let's say we have this code, and how it's, and now what buffer deallocation is doing, which is basically it's inserts clone here, and then somewhere later it inserts and in this case we can safely convert clone to just incref.
In your model where you have like ref counting, you could use clone for hacking this, but in the semantic model of memref, like the %0 should be dialect as well, right? Separately.
Yeah, and
And 0 is dialect separately. That means %5 has to be a different piece of memory than %0, which means the clone has to make a new copy. And also, like, nothing guarantees that, like, for example, if I don't know if clone is a copy or not, how do I know if I could insert a write line 10? Or even for the purpose of alias analysis, right? That's if you don't know if clone is a copy or not, that means you have a may alias between 5 and 0.
So yeah, clone doesn't have any view interface attached, but when we are converting it to retain actually have a view interface, so alias analysis will work. So I'm not sure about like the general clone semantics, but I think the way that currently the only way we can get this clone generated is by buffer dialog pass, and I think at least for this case it always follows this semantics, or at least we didn't find any examples when it doesn't work for
I'm going to look
us.
up right now, and I don't even find a clone operation. So is it still here? Oh, it's a bufferization.
Maybe yeah, moved to bufferization.
Yes. Okay, so now it makes more sense because it's specific to the bufferization, and the bufferization dialect is like exists because of specific issues like the one we're talking about. So it makes sense.
Okay.
Yeah. I think we moved it to bufferization because of the discussion we're having, where it was like, this is really weird. You have to really understand the context in which dir is in a weird state to be able to make sense of what's happening. So anyway, makes sense. Looks good.
Okay. Okay, and there are some other additional advantages to have a separate like control block struct, and to which we can potentially like attach some additional information. For example, there were some discussions how to handle like memrefs which are returned from the functions, because we cannot just deallocate them, because for example it can be memref pointing to some global data and it like will break. But when we have this control block, basically we can have a flag in this control block which says like this is global data, don't touch it, don't deallocate it, and we still can have a consistent model when we are calling deallocate on each memref return from the function, and it won't crash.
I think it's a nice solution that you found. It's a really smart way of using the difference between the allocated pointer and the data pointer in the descriptor. It's pretty cool.
Actually, yeah, the one the one issue was that this allocated pointer was typed pointer, and it was type like the memref data type. But now everyone moved to the APAC pointers, so it's, and we had to insert like bitcast previously, but now everything moved to the APAC pointer, so we don't even need to like change type of this pointer or insert bitcast.
Sorry, I missed something. Which opaque pointer are you talking about?
Oh, so now these pointers in LLVM, when we are leveling this to LLVM, they are just PTR without any type attached. But before this switch happened, this pointer was type like
Got it.
float,
Got it.
float or integer.
Yep, I see. Simpler now, right?
Yeah.
Okay.
I wanted to create a pull request to change it to something like general, but they eventually, but I never had the time, and eventually this entire APAC pointer switch happened and problem solved itself. Okay, so a few more. So in our Ntensor ops, we are supporting tuples as the arguments to the our Ntensor ops, and we are using built-in tuple type, but we added, so, but upstream doesn't have any actual ops to manipulate on tuples, so we added a couple of our ops, basically just build tuple, which like takes a list of values and return a tuple, and tuple extract, which takes a tuple and in the index and then return corresponding value from tuple. Yeah, CDNS. So again, our NumPy dialect is high level, and on this high level, we are operating actually on signed and unsigned integer types. So we keep sign for some time, but as we are lowering it, we are eventually converting them into like signless, as is everything all low-level dialects expect signless integers. So for this, we have our sign cast op. I think it can be useful in upstream too. Okay, and last part, we have our custom loop fusion on SCF parallel, but basically, so there is a function called and pass called naively fuse parallel ops in upstream, and it's naive and it doesn't like, it don't do a very like strict checks on array on like memory of aliasing and such. And basically what we did, we take this path and updated it to use actual alias analysis from alias from the MLIR to properly check if we can fuse things or not. And it works actually reasonably well for us. And I'm not actually sure if this upstream path is used by anyone. So, but if anyone interested, we can try to upstream our changes. And yeah, so yeah, we have a repo, a public repo for our work, and also we have we are uploading. We don't have a proper releases yet, but we are uploading CI artifacts to the Anaconda channel. And basically, you can install them using conda, like single command, and test things. And that's all for me. We're almost on time. 2 minutes left.
Awesome. One thing I forgot to ask, I didn't want to interrupt at the time you were mentioning it. You have a path that will restructure the control flow from CFGs. Is this generic enough that it could be upstreamed? I think it would be probably interesting to quite a few people.
Yeah, the one thing which is missing upstream is that we need the op to create basically. We need the op to create an uninitialized values. We have our custom undef op, and there were discussions on poison. I think poison op in upstream, but they are not didn't get far. So as long as we have this like as a undef or poison op upstream, we can upstream this path as well.
Makes sense. Fantastic.
And actually this like poison op will be used. We have a few more like some other passes when where we are using this undef op, our undef op. So if poison is added upstream, we can try to upstream those passes as well.
And that's it for today. Thanks again, Ivan, for presenting this very interesting work on Numba. And I'm looking forward to see more of it and continue the discussion about everything that can go in MLIR and that you can upstream. And thanks everyone for attending, and see you next time.